In this lesson, we're going to talk about signal propagation speed. And electronic signals propagate at the speed of light. And the speed of light is 186,000 miles a second in the air. And we can go through the conversion of 186,282 miles per second, and so on and so on. That works out to 11.8 inches per nanosecond, or approximately 1 foot per nanosecond. And as I said, that applies in the air. In any other environment, signals slow down and the speed of light slows down. And the speed of light slows down by the square root of the relative dielectric coefficient of the material. So the speed of light would be 11.8 inches per nanosecond divided by the square root of the relative dielectric coefficient. And virtually all materials have dielectric coefficients, and you can look them up in a variety of different handbooks of physics and chemistry and so on. Well, in FR4, the relative dielectric coefficient is approximately 4, and so the speed of light is 11.8 inches per nanosecond divided by the square root of 4, which is approximately 6 inches per nanosecond. And that's the rule of thumb that we're familiar with. Signals on our boards travel at approximately 6 inches per nanosecond. That comes from this kind of analysis that we just went through. It's an approximation, but it's a pretty good approximation. We can get closer if we need to. This is an illustration I like to use in some of my seminars. I took this photograph down by Bend, Oregon. It's really pretty country down there. And then let's imagine that I erected 4 posts out there, and I strung some copper wires between those posts, and I constructed this in such a way that these copper wires are the same length. Now, I'm going to inject a signal at one end of these copper wires, and I'm going to measure the time it takes for the signal to get to the other end of these copper wires. And what I would do is I'd ask the class to tell me which wire or which situation the signal is going to reach the far end faster. I did have one student tell me one time that, well, this is a trick question because everybody knows the water's going to short out the wire and the signal's never going to get to the far end of this one. And, while I am not above using trick questions, that's not the situation in this case. The answer is the signal is going to travel much faster down this wire and get to this end much quicker in this case than it's going to in this case, because in this case the electromagnetic field around the wire has to travel through the water. So the environment is the water. The relative dielectric coefficient of water is approximately 81, depending on what kind of assumptions you want to make. The square root of 81 is 9. And so the signal is going to propagate about 9 times slower through a wire in water than it's going to in the wire in air. So what this illustration emphasizes is that the propagation speed and time is not determined by how fast the electrons can move through the conductor. It is determined by how fast the electromagnetic field can move through the medium that it is flowing through. And remember back to the illustration in lesson 1.4, where we showed the impact of width. Here we have an 8 mil wide trace. Here we had an 80 mil wide trace. In the 80 mil wide trace situation, a lot more of the electromagnetic field is captured in the dielectric. Here, a lot of the electromagnetic field is in the air. So in this case, with a narrow trace, the signal will propagate a lot faster because a lot more of the electromagnetic field is in the air, which is a faster medium. Here, the propagation speed is going to be lower, it's going to be slower, because so much of the electromagnetic field is captured in the dielectric. Now, the propagation speed in strip line, as we said, is 11.8 divided by the square root of the relative dielectric coefficient in inches per nanosecond. The propagation time in strip line is simply the inverse of propagation speed. So it's the square root of the relative dielectric coefficient divided by 11.8 nanoseconds per inch. It's easy sometimes to get confused in terms or to be careless in terms when we're talking about speed and time of electromagnetic signals. Propagation speed is faster in microstrip because part of the electromagnetic field is in the air. Therefore, propagation time is shorter in microstrip. The calculations are a lot more complicated in microstrip because there's so many variables. Now, I did a little study that is reported in my book, PCB Currents, on page 31. It's also reported in more detail in an article on the UltraCAD web pages, Microstrip Propagation Times Slower Than We Think. So I'm not expecting you to pick up this relationship from this slide. If you want to know more about this in more detail, go look at these two references. But if you want to determine what the propagation time in microstrip is going to be, there actually is a way to do it. And the propagation time is a fraction times the propagation time in strip line, which is this relationship. And that fraction is given by this relationship, which is a function of the natural log of the width and the height and relative dielectric coefficient. So this is a complex formula. As I say, I've gone through the derivation in this article. But the bottom line is, if you really care about accurate propagation speeds and times, put your traces in a strip line environment. There's two types of timing issues on printed circuit boards. One is how to set the exact propagation time for a trace. The second is a little bit easier, and that's simply how to match propagation times for two or more traces. We have two or more traces, we want the propagation times to be the same, but we don't necessarily care exactly what that propagation time is. Now, some high-end design tools will do these calculations for you using field solver techniques. That's the easy way. That's what you should use if you have those kind of tools available to you. Setting the exact propagation time, well, if you need to do that, use a strip line environment. Ensure that the environment is homogeneous. I'll talk about that in a second. And you do have to know the relative dielectric coefficient with some degree of precision. And that's not as easy to know as we sometimes think. As a little aside, I will tell you once that I took a tour of a fabrication house, and I was taken on the tour by the director of quality control. And when we went into the room that housed the inventory, I looked at him and said, if I specify a board with a relative dielectric coefficient of 4.3, where is that? And he pointed to a shelf in the room. I said, okay, now if I specify a relative dielectric coefficient of 3.7, where is that? And he pointed to the same material on the same shelf. I was somewhat dismayed that they weren't going to pay any attention to what I specified, and that is a problem for us as designers to actually know specifically what the relative dielectric coefficient is. But then, if we do have control over these three things, well, then the propagation time in strip line is given by this formula. And I like to say that this is a good formula in the sense that this will give you a pretty accurate, pretty reliable answer that you can depend on. If we want to match propagation times for two or more traces, well, then we want to route the traces in an identical environment, and we want to route the traces the same length. And that's subject to the timing tolerances set by the system design engineer. What we mean by the same, there'll be a tolerance on that, except when we're designing differential traces. And when we get to that lesson, I'll explain why we do want traces to be the same length in differential traces, even tighter than perhaps the tolerances set by the system. And that has to do with the generation of common mode signals and common mode EMI. But we'll get to that in another lesson. When we talk about identical environment, that can be kind of tricky. If we're talking about really fast signals with really fast rise times, and we have a dielectric with a fiber weave that looks something like this, and now we have these two traces that are routed in there, these two traces are not in the same environment. This trace, at least over this range, is 100% over the fiberglass weave. This trace is over 50% fiberglass weave and 50% rosin. And the environment might be different for this trace compared to this trace if our rise times are fast enough. So understanding what is meant by and what consists of an identical environment can be kind of a tricky situation. So the takeaways from lesson 1.5. Propagation speed and time is determined by how fast the electromagnetic wave can travel through the material it is traveling through. It's not determined by how fast the signal can propagate down the conductor. And the propagation speed and time is more easily controlled in strip line environments because there are fewer variables involved.